Welcome back. So we're now going to move on to quantitative methods to measure the amount of error within a forecast. And that's going to enable us to have a fair comparison across multiple methods and pick the best method for forecasting our time series. So there's a number of things we need to learn about in order to do that. The first is how to split your time series into a training set, so that's data you use to build your model, and a test set, and that's data you hold back that your model hasn't seen that you test your forecasting ability against. We're going to look at the definition of a point forecast error and then how you can have different types of measure to quantify that. So we have some scale dependent measures such as mean absolute error and relative errors such as mean absolute percentage error that we can use to quantify that error. And then finally we're going to look at how in-sample error is nearly always smaller than out-of-sample error. And all that means is that predicting the data your model has already seen is always more accurate than trying to predict data that your model hasn't seen, so data from the future in a time series. So we're going to read in our standard libraries, NumPy, Pandas, Matplotlib, Seaborn, and then we're going to work with the ED data set again. So here I'm going to read that into a Pandas data frame and then do a calendar adjustment. If what I'm saying here doesn't make sense, then I suggest you go back to previous lectures to learn about reading data in as a time series and doing calendar adjustments. So what we're seeing here is that the data is of length 98. So there's 98 individual observations within that ordered time series. So in a real forecasting problem, when you read your data in, the thing you must not do is look at the whole time series straight away. That leads to bias and overfitting. My advice to you is to always read it in, understand how long that time series is, and then split that data set into training data and into testing data. And that testing data needs to be kept safe because it's your only opportunity to simulate a real forecasting scenario. So you want to be able to select your data, select your model, and then test that in a real scenario to see how good you expect it to be. So to do that, we do what's called a train test split. So the training data is the data you use to build your model. It's the data your model sees, and your testing data is the data that your model does not see. You hold that back and keep it safe. That's really straightforward to do in Pandas. There's a couple of ways to do it. The first is to call the iLock function of a data frame object, and that allows you to use numerical indexes to split your time series. And the second way is to use a date and say I want values in my training set before this date and values in my test after this date. And it's entirely up to you how you do that. I'm going to show you both ways of doing it. So the iLock approach is just a couple of lines of code, just to remind ourselves that there's the length of the time series is 98 altogether. And to work that out, I called the shape property. If you index that with 0, you'll just get the value 98 there. So then you can use that to calculate how long you want your training data to be. I want to predict the next 12 months, so I've taken 98 and subtracted 12. And that gives me my training length. What you can then do is you can call from your arrival rate data frame the iLock command, and then that returns the index, and you can slice that index as you would slice a NumPy array or slice a Python list. So I'm going to slice from the beginning of the series up to and excluding the training length. And then what I'm going to do is I'm going to slice from the end of that training series all the way to the end, and that's going to give me my test set. So when you've got all of it on one line like this, if you've not seen that before, and where I've got train, test, that's called tuple unpacking, and is kind of a clean way of writing your code. So let's just check the length of those. So we had a training shape of 86 after that, and a test shape of 12. So it's give us the train test split that we wanted. The second method is if you want to split by a particular date, and well, to be frank, you can't be bothered to work out what number that is within the time series. So a simple way to do that is to not use the ilock, but to use the lock command, and then into the square brackets, you're pasting an inequality. So I've got here the arrival rate dot index is less than that split date, which in this case is 2016-06, and that gives me my training data. And then my testing data is given by when the arrival rate is greater than or equal to 2016-06. So if I run that, and let's have a look at the shape of those data frames or data series that have been returned. And again, we've got the same shape. So two options for doing it. And which option you use is entirely up to you. So just a reminder, do not look at that test set. It's that we sometimes call that a holdout set. So we're holding back a proportion of the data that we want to use in a simulated forecasting scenario, and we want to check the model's accuracy at predicting that unseen data. So let's have a look at the training data only. Okay, so hopefully this is fairly familiar to you now. We know we've got an upward trend in this data set, and from previous analyses, we know that there's some seasonality within there. So now we're going to move on to make forecasts, which we've done before. What perhaps wasn't clear is that we are producing what's called a point forecast. Now actually, because there's uncertainty in the future and that these are statistical models, what you're producing is a forecast distribution. And we'll talk more about other values within that distribution in a later lecture. But for now, we're going to focus on the mean value within that distribution, and we call that a point forecast. It's what our model thinks is the most likely value of that forecast distribution. So if we create a seasonal naive model of seasonal length 12 and look at the predictions, these values are the mean values of the seasonal naive forecast distribution. So one way to measure forecast error is to measure how close those point forecasts are to the observed values. So we use the test set for that. So we make a prediction 12 months into the future, and we have a test set of length 12, and we can compare those two values. So one way to do that is to just look at the difference between the forecasts at the correct forecast horizons, and then take the average. The issue with that is that forecast errors can both be positive and negative. So sometimes they are above the actual value and sometimes they're below it. So this positive and negative aspect means that the average value of the errors will just mask the true size of the errors. It won't give you a good feel for how accurate a forecasting method is. So because of that, there's a large literature on how to measure forecast error or point forecast error. Now, each of these measures has its own pros and cons. I'm going to show you some of the most common ones used and some of the issues with them. It's then up to you what you use. You might find that it's context specific, which one you should use, and it might also be a case of what forecast error measure do your stakeholders understand in practice. So the first type of measure we're going to look at is a scale dependent measure, and that's the mean absolute error, and we're also going to look at the mean squared error. So sometimes in the literature you'll see that people have done the median absolute error or the median squared error, and there's a bit of a debate about whether you should use the mean or the median, depending on the skew of your on distribution of your errors. But for here we're just going to focus on the mean. So there's some ready-made functions to calculate for you in scikit-learn. So from sklearn metrics you can import the mean squared error and the mean absolute error. So what the mean squared error and the mean absolute error are trying to do is deal with this problem of some errors being positive and some errors being negative. So the mean squared error takes the errors and squares them. So that gets rid of the problem of some of them being negative. It does mean that the units of your error measure are squared, which is sometimes a bit confusing. So you have quite a large number with unusual units, and that can be quite difficult to explain to a stakeholder. Mean absolute error, on the other hand, simply takes the absolute value of your forecast error, sums them all up and takes the average. So let's have a look at what that looks like for our seasonal naive model. So if you remember, we've created a seasonal naive model, fitted our training data, and we've predicted 12 months into the future. And these were our predictions in a variable called preds. We also have a test set. So let's look at the mean squared error from those predictions. So our mean squared error is 284. So that is 284 out. And if we look at our mean absolute error, that comes back as 15.13. So on average, we are 15 people out on the daily number arriving at the emergency department. So you can see straight away from the way I explained that mean absolute error is a much easier error to explain conceptually. So not all is lost with mean squared error. So because its units is squared, one simple thing to do is take the square root of it. So that's called the root mean square error, and you see this used a lot. So effectively we've squared all our errors, taken the average value, and then we take the square root of that. So we can do that using NumPy. So if we say numpy np.square root and then passing the result of our mean squared error, we get the root mean squared error, which is 16.8. So you can see that mean absolute error and root mean square error have the same units, but they return slightly different absolute forecast error values. So here we can see that root mean square error is saying that on average your forecast is slightly worse than what mean absolute error is saying. So you can report a range of these error measures if you would like. So they're scale dependent errors. They give you forecast errors in the units of whatever it is you are measuring. But sometimes it's useful to have have measures that don't depend on the scale. So an obvious choice would be some sort of percentage error, and that's what mean absolute percentage error is trying to do. MAPE, you'll hear that called MAPE in forecasting textbooks and in forecasting literature. And this can be quite an intuitive measure to talk to a manager or a stakeholder about. So for example, on average our forecasts are 3% off, is quite useful. So that's really simple to calculate. You're looking at the percentage difference of your forecast from your observed value, and then you're taking the absolute value so that you get rid of any negatives, and then you're taking the average of that. So Pencord has implemented mean absolute percentage error for you in the forecast.metrics module. So you need to import that. And then we can basically call mean absolute error, and we can pass in our true values, which is our test set, and our predictions, which is our seasonal naive predictions in the variable preds. So that's telling us that on average our forecasts were just over 4% out. So there is an issue with MAPE in the sense that it's not symmetrical. Okay, so I'm going to give you two examples here of where the forecast is the same amount different from the observed value in absolute terms, but in one case it's below the observed value, and in another case it's above the observed value, and we're going to see that it gives quite different percentage errors. So in the first scenario, this is how we calculate MAPE, or absolute percentage error. It is our observed value yt minus y hat of t, which is our predicted value, divided by our observed value, and we take the absolute value of it. So that gives us our absolute percentage error. So our first scenario is that our observed value is 150 and our predicted value is 100. So in this case, our predicted value is less than the observed value. So when we calculate that, your numerator is 50 and your denominator is 150, so you get an absolute percentage error of 33%. In our second scenario, we swap things round. So the difference is still 50, but in this case, the predicted value is 50 greater than the observed value. So our numerator is 50 and our denominator is 100 in this case. So our absolute percentage error is 50. So in cases where the prediction is less than the observed value, you get a smaller absolute percentage error. So this tends to lead to picking models that under forecast. That means models that tend to produce predictions which are less than the observed values. So that's something to bear in mind when you use MAPE, and it's another reason why it's useful to have a range of forecast errors that you use. So as well as MAPE, I would always recommend using something like root mean square error. So finally, let's have a look at the difference between in-sample and out-of-sample errors. So if you remember, in-sample errors are to do with predictions your model will make against data it's already seen. So intuitively, you would expect the model to be quite good at predicting those values. So we call those errors the model residuals, the difference between the fitted values of the model and the training data. So let's just have a look at so SNF, if you remember, is our seasonal naive model that we created earlier. And then underscore fitted is the fitted values that we can access from that object. And we're just going to look at the tail end of that, the final 10 values in the time series. So these are the dates that we're looking at, the final 10 dates in the time series, training data. We can see the actual value, we can see our predicted value, and then the final column is called resid, and that's the difference between our actual value and our predicted value. So these are our in-sample errors. So there's different ways to get at those values within our baseline forecasting methods. So If you want to just look at the fitted values, you can call snf.fittedValues, all one word. And that returns a pandas series with all our fitted values. These initial values are not a number, nan, because if you remember, seasonal naive is taking the previous 12 values and bringing them forward. So you can't do that for data that doesn't exist. So at the start of the time series, we don't have any data before that, so we can't bring that forward. So the first 12 values in a seasonal naive forecast, fitted values are always not a number. And also we can access the residuals by .resid. So the errors, the forecast errors in sample with .resid. And again, the first 12 of those will be not a number. So what we're going to do is we're going to calculate the mean absolute error of the in-sample fitted values. So our true values is the training data rather than the test data this time. We've dropped the first 12 values in that because if we don't have that within seasonal naive predictions. And then our Y predictions are our fitted values. And again, we drop the first 12 because we don't have any predictions for that data. So let's run that. So our mean absolute error is just over 11 for the in-sample. Now, what was our out of sample? Well, that's our forecast. So if we run that, as a reminder, our mean absolute error of our forecast, so comparing our predictions to our test set, was 15. So what that shows us is that our in-sample error is smaller than our out-of-sample error. So you must never judge the forecasting ability of your model on how well it fits the training data. That's a really crucial point. If you make that decision, you might find that your actual forecasting ability is significantly worse than that. And there are instances where using the in-sample error, how well your model fits, to choose your model will lead to you picking the worst model, or at least a model that is not the best. So be really careful about that and think really carefully about, am I evaluating my in-sample errors or am I evaluating my out-of-sample errors? So as a little bonus, let's compare all of those forecasting methods using a holdout set, a test set. So we've got our baseline methods: average, naive 1, seasonal naive, and drift. And I've got a little convenience function that will read those in called baseline estimators, which is in forecast.baseline. So all I need to do for baseline estimators, the function is I pass in the number of seasonal periods, which is 12, and it returns this model object. Let's have a look at that. So these curly brackets means that what baseline estimators has returned is a dictionary. So let's just have a little look at what it says. It returns a dict, of forecast objects. So what we can see here is the name of the forecasting object. So naive forecast 1, seasonal naive, average, drift, and ensemble. And then the type of object. So for NF1, it's forecast.baseline.naive1. So just a little extra note on what ensemble is. So ensemble in this case is the average of all of these methods. Just because sometimes taking the average of multiple methods leads to a better model. So you don't need to fully understand the code I've got here, but this is just a quick way of looping through all of those models. So each time we loop, we fit the training data, we make a prediction, and we calculate the mean absolute error. So I'm going to do that for all of those models and then print out the model name and the mean absolute error. So my 12-step mean absolute error for all of those different methods. And then we can look at that and we can pick which of those methods has the lowest mean absolute error for our out of sample forecast. And what we can see is that naive forecast 1 has by far the lowest mean absolute error. So in this simple case, I recommend that we choose naive forecast 1 as our baseline method. Now this process, this simple train test split and then calculate point forecast errors, works for any complex forecasting method. So you would do this first, and then you would go and calculate those forecast errors against a more complex model, and you would see, does that beat my baseline of naive forecast 1? If it doesn't, then I don't take that forward.